Okay, so thank you for inviting me. So as I told in the introduction, I'm a pure mathematician, but in fact, I'm always very curious of what I don't know. I teach to pre-service high school teachers, so I'm very interested in education. I give public lectures. I go in the school or colleges to give lectures. So my lecture is very practical. Instead of going into generalities, I think Fred drew a very broad spectrum. In fact, I will go even broader than what he said. So I will more go into particular examples of things we can bring, and you will see that it's a mixture of things we can bring to the public. Well, just under the question, what is mathematics useful for? Something we have to defend all the time. So some examples, and how we can motivate. In fact, Fred was saying, how can we motivate the undergraduate to stay in mathematics, but how can we motivate the kids in the school to go in mathematics? And we have to give answers. I will go with examples. So, and in fact, examples sometimes that you can do in your classroom. For instance, a question, well, what would be the rise of the oceans if all glaciers of Antarctica and Greenland were to melt? So you go to internet and you find some data, the area of glaciers in Greenland, the volume. In Antarctica, I just found the area. The thickness is very high, so I took a mean thickness on 1.6 kilometers, so 1,600 meters. And then, so that gives you a volume. Then you find on internet the area of the oceans, and you divide. So the volume of the ice sheet divided by the area, you find approximately 75 meters. So when I first did that, I said, well, where is the mistake that I made? And then I went to internet, and I found other people that had found the same thing, and I discussed, and there is no mistake. So what are, of course, so then you can start the discussion in the classroom. What are the limits of the model? Well, maybe some of the water may evaporate. But then, will it increase the rainfalls? Maybe some of the water would enrich the groundwater. Always in the room, some people say, oh, but part of the water will go over the land, so that will be less over the ocean. And then, okay, always when we talk of something, what have we missed? Which is one of the messages. We are thinking of some things, but we can make predictions with what we have thought of, but have we forgotten some important things? I will just discuss a little, for instance, this part. So, well, the percentage of the area of Earth that's covered by the ocean is approximately 70%. The mean altitude is 840 meters. That's all data you find on internet. So in the classroom, you just go on internet and you just have the discussion with these things. So with this altitude, you can imagine that no more than 1/4 of 30% of the ground would be covered by water. So 75% of the surface of the whole Earth. And then instead of 75 meters rise for 70% of the surface of the Earth, you would go to 77.5%, while you just go down to 68 meters. So we have a big, big potential rise. Well, we hear on the news that the rise would be of the order of 1 meter till 2100. So in fact, I asked some Hervé Letrut, some very well-known climate scientist in Paris, and he just told me, well, because the ice cannot melt so fast. But you see that the official message is they will just tell the rise by 2100 will be of the order of 1 meter. So it's something that's hidden. They then tell us what's coming. In fact, when we'll be by 2100, the steep will be stronger than now. So in fact, if you are to build your dams and things, you shouldn't build for 1 meter. You should build for much more. So we see that we must look beyond 2100. And in fact, One question I will say, what haven't we put in the model? I was last September at the General Assembly of the International Council of Science in New Zealand. The International Council of Science is very concerned with climate change and all these things. So they work very hard on this. And there was a lecture that impressed me a lot from Butler, her name, about one new hypothesis is a potential collapse of the West Antarctica ice sheet. So the ice is so thick in Antarctica that the level of the land is below seawater. So you could imagine that you have seawater that could go underneath the ice and break some big part. And if you have, once the ice is melting, it's like water on the ocean, it rises. So if the West Antarctica ice sheet were to collapse, and this is a question mark, that could mean a rise of 4 to 8 meters by 2100. So that's things we can. Now I'm out of climate change, it's just a movement of tectonic plates. So they move on viscous magma, and mathematics helps understanding their movement. So there are 12 big plates, and now we're identifying more, so more than 50. I'm just interested to the mathematics behind. So how to describe the movement of a tectonic plate? Well, it's a solid. It's a solid on a sphere, so it's a rigid movement. And then it's slow movement. So if it's a slow movement, a rigid movement of a sphere, then it's well approximated by a linear transformation, which preserves distance and angle, so an orthogonal transformation. And because it's close to the identity, then it is a rotation around an axis. So the movement of, so if you want to describe a rotation, then you have to find its axis. So its axis would intersect the Earth at 2 points, and then you have an angular rotation. So it's going to, so you see that you can, the movement, well, what you have is, here you would have, for instance, the green, you would have an axis, and you have the rotation movement, and that gives you the motion of the tectonic plates, and that you can have the different types of faults. So divergence when plates are moving apart. You can have convergence, and you can have slides. It comes with the drift of continents. So the slides, the images are in French. So Wegener, Pangea, the hypothesis is that the continents were once all glued together. What's interesting is where the theory relies on. And then you have some marking from ancient glaciations. So why would the glaciations go like that? It's not natural that they would go inland. Well, with the image of the Pangea, then it becomes more natural. There are some similarities in fossils in regions that are far now from each other, and also correspondence between the geological structures. So now we have these geological structures. Look at these two small pieces of mountains, and when you draw the Pangea, then they fit exactly like that. So I move from different questions. So evaluating the mass of the Earth. So you use Newton gravitation laws, and you deduce the mass of the Earth from the gravitational attraction. You know that the attraction is the acceleration 9.8 meter by second square. And you know the universal constant, so you find the mass of the Earth. You know the density near the surface, it's between 2.2 and 2.9 kilogram by decimeter cubes. And you calculate the mean density from the volume, which is 5.52. So that means that what that tells us is that the interior of the Earth is much heavier than what we observe at the surface. when I have this kind of problems and I go to the public, I say, okay, that's like, I don't see what's inside the Earth. But then what I do is that I put my mathematical glasses, and then I understand, I can see inside. Then the Earth is very heavy. So it tells us that the interior of the Earth is very heavy. So in fact, putting our mathematical glasses, this is used to discover the Earth's interior. So when you want to discover the Earth's interior, you just study the seismic waves and what they tell you on the surface. So you have two kinds of waves. You have the pressure waves that travel through the viscous interior, and you have the shear waves that are damped in the mantle, and then you don't record them far from the epicenter of an earthquake. So that tells you that, in fact, the interior is viscous, because otherwise you would register the shear waves very far from the epicenter. So going further, in fact, for the people who want the details, I have written an article in the College Mathematics Journal of the MA. So Inge Lehmann would use the seismic waves to discover the inner core of the Earth. So it's interesting as a story because she's a woman mathematician, and so it's a discovery she made in 1936. So if you have, suppose you have an earthquake here, and you have, if the Earth were uniform, then the waves would travel like that, and then you will record them at different stations, and then you know, okay, suppose you know the time, then you can measure the travel time. So you will get a travel time like that, depending of the angle where you are. But it's known that the Earth has several layers, and when we change layer, well, the signal would make an angle according to the refraction law. So this is what occurs. So when you have the mantle, so this is the baby model from Inge Lehmann. So she took a speed of 10 kilometers by second in the mantle, and then you enter the core, and you slow down to 8 kilometers. And then so the waves are bent like that. And what you see is that, in fact, because of this, so you have the tangential one, and then in these regions, you should record no signal. So no signals are detected, so in her toy model, between the angles, so from the center, so 112 to 154 degrees. So that means that from your epicenter, you have an annular region where you should record no signal. Also, the signal, the travel time is discontinuous. You see, for instance, here you can have some signal like that, but you can record another one that would be refracted. So this is why we could have signals arriving at two different times. But then she discovered that there were signals registered in the forbidden regions. And then what she did was she had an inner core here, and in the inner core, the signal travels faster. If it travels faster, then if you arrive with an angle, you are going out, and if you arrive quite tangentially, then you will be reflected. And because of this inner core, then you could register some signals in the forbidden region. So in fact, in the refraction law, so I will just have an animation. So if you arrive, so here you are slower and you go to faster. So when you have, it tells you that in the second region you should have the sinus of theta 2, which is equal to this quantity. But if this quantity is greater than 1, then you have no solution, and then the signal is reflected. So as you see, the material, when we discuss this example, then we are working around reflection and refraction. I'm changing subject. So the shapes of Earth. So it's the loss of stability. Suppose you have a flat land with sand. So it's very, very flat. And then you have the wind that starts blowing. Well, you have it with snow also. And then, so then you may have a small irregularity, and then it starts growing because it stops the sand. So in fact, when you will always have wind at some time. So on Earth, you never observe some flat area of sand, and it will create regular patterns, so dunes, waves, vegetation patterns. So it's a very recurrent theme in science. So it's a very important. This idea of terrain occurs in many, many areas of science. In fact, it was his hypothesis for morphogenesis. So this is why it's important. So it's nice to introduce the idea because it's so general and unifying in science. A model that would explain the sparse vegetation pattern here. So you don't have enough water for uniform covering with vegetation, and then you have some feedback mechanisms. So in fact, when you have some small patches, well, they can drain the water with their roots. They can drain the water from the neighboring empty spots. And also, well, when you have vegetation, so it limits the evaporation. So it will stay, when you have a little water, it will stay more humid. So the model generates some patterns. So you could have spots, labyrinths, gaps, and you could have stripes. Well, these patterns are exactly observed in nature, the spots, the labyrinths, the gaps, and the stripes, you have them on slopes. So you get what's very interesting, what just you want to attract the public, it's that the same model works for the patterns observed in animal coatings, and then you have the spots. So this I found on internet, so don't look at but you have the labyrinths, you have the gaps, and you could have the stripes. So you have, I think the great idea to present is the unifying idea. In our vegetation, so we observe the hysteresis phenomena, so you have humidity, you have vegetation, and then you can have, in this region, bistability, so you can have either an equilibrium with no vegetation at all, or you can have the gaps, the labyrinths, and if you have more humidity, you have the spots, the labyrinths, and the gaps. The lesson from this graphic is, suppose for some period, the humidity, you have a drought period, so then you lose your vegetation, it dies. So you come back here, and then when the next year the humidity comes back, the vegetation doesn't come back. You need to go very, very far to be able to come back. So a very important idea, which is very general. So we have passed a tipping point, no return is possible. And the idea of a tipping point is again a very unifying idea when we present some modeling. When I was preparing public lectures about mathematics of planet Earth, so there were the 4 teams, and one team was a biologically diverse planet. And then I was saying, okay, I wanted just one element for the public to present, and was wondering, okay, so you know. And so then I discussed with some biologists, and this is the theme that I liked and that I choose for the lecture. So Earth is inhabited by millions of living species, and then where does all this biodiversity come from? So just understanding the mechanism that produces the biodiversity. So of course, you have mutations, randomness, create new species, and then these species interact to survive. So when we present modeling, we present small models, predator and prey, so we can have cycles of, probably I don't go into the details. We can have competing species, so in weak competition, we can have that the two species survive. But in strong competition, we see that there is like a frontier, and on one side, species 2 wins, and on the other side, species 1 wins. So in fact, the lesson from this is that strong competition for one resources leads to the extinction of one species. And this has been generalized by Simon Levin. So the lesson is that competition goes against biodiversity. So that means if the question is what maintains biodiversity, we should understand it. So there are other forces. So one is spatial heterogeneity, where you may not have the same initial conditions in different places of the planet. Another one is temporal heterogeneity. Well, the conditions are not always the same. You can have one species that's favored by winter, another one that will be more prosperous in the summer, and one that will suffer from the drought, another one that will suffer from too much humidity. So because of the changing of conditions, this allows. But the very important force also that was introduced was cooperation. So it's illustrated by the prisoner's dilemma. So I'm individual 1, and you are individual 2. And we have two choices. We can choose to cooperate or to remain silent. So suppose you choose to cooperate. If I cooperate, I get 2 years in jail. If I defect, I get 1 year in jail. Suppose you choose to defect. If I cooperate, I get 4 years in jail. If I defect, I get 3 years in jail. So whatever you do, my best choice is to defect. Okay, but maybe you will make the same reasoning that I did. So maybe you will choose also to defect. So then we will both defect. Then we will both get 3 years in jail. Maybe we should have cooperated. So in fact, that's the kind of things the nations are facing with the climate conference next December in Paris. This is well illustrated. So I won't go into the details because time is passing, but Martin Nowak has really observed 5 mechanisms in the world that that means that the natural species do in fact cooperate, and this is important for biodiversity. The lesson is that cooperation has modeled the world as we know it, so it explains the preservation of biodiversity, and it's everywhere present in the human organization of the planet. I'm almost out of my time, so I won't explain the next slides, but just say the title. Now I go on many things. So the Greek that could measure that the Earth was round and the size. Funny question, so how many turns does the Earth do during 1 year around the sun? Well, during 1 day, you need to make 1 turn around your axis, but then a little more because you move here. So you make 366 turns during 365 days. Mechanism of the season, so that's most students in school don't know that the mechanism of the season is because the axis of the Earth is slanted. So in fact, we just, when we do this in our mathematics course, we just fill the gaps in their culture. The height of the sun at noon, depending on the latitude and the season. So of course, you wouldn't be surprised that at your latitude, the curve is like that. What is interesting is to have the curve when you are between the tropics. And then you see that, for instance, at the equator. So you have 2 maximum and with a sharp slope. So these curves are interesting. The equation of time. Have you already noticed that in the northern hemisphere, the sunset is sooner on December 10th than on December 21st? So 21st is the shortest day, but the sunset is later on December 21st than on December 10th. So this comes from the fact, it's called the equation of time. Well, here I have the data for Dar es Salaam. When you look to the solar noon, well, the time changes by an order of 30 minutes during a year. So it's a mathematical problem to give an explanation for that, but I don't have time. GPS, so how does it work? So it's what is your distance from a satellite, and when you have this, then you can calculate where you are. So you are at a given distance from a satellite, so you are on this sphere. A given distance from this satellite, so you are on this sphere. The two spheres intersect on a circle. You are at a different distance from this satellite, so you are on this sphere, which intersects in 2 points. And then you choose the point that's close to Earth. Some non-standard applications, so it's used to synchronize electronic equipments, because in fact you need more than 3 satellites, you need 4, because the clock of your GPS is not the same as the clock of the satellite. So your receiver calculates the shift between its clock and the clock of the satellite, and when it has done this, you can use it to synchronize electronic equipment. All electric grids are synchronized by GPS, which are much cheaper than atomic clocks. That's how you measure the displacement of tectonic plates, and you measure the growth of mountains. Maybe I should stop here. Okay, well, how you give definition? What means altitude if the Earth is not a sphere but a geoid? So altitude, so in fact you use altitude, well, some constant altitude. It's a level surface of the gravitational field. And then for altitude 0, you choose the level surface that best approximates the surface of the ocean. So that gives the role of mathematics on how you give definitions in some other scientific disciplines. Then I have other things in cartography, so how you make maps, but I will stop here and we'll have more time to discuss other ideas during the workshop.
Suzanne, how much time do you think we... Okay, all right.
Christiane, are these slides going to be available to us so that we can put it on the website, please?
Of course, I will.
Anyone else?
So, how did your students that you presented, the first example with the 75 meters, how did these students respond when the 75 meters first came up? Were they shocked? Did they have any idea how high 75 meters are?
This one I haven't done with the students. Several of the things, it's because I teach a course, mathematics and technology, and the students have to do project. And then I would, so for instance, the projects with the season, with the equation of time, why it's not noon always. These are parts of the projects that the projects could be on technology, but I found that all these things are interesting projects. I could say the rise of 75 meters, I had done it when I was, well, we were having this competition, and I was just, and I put it on the blog of MP, but it could get unnoticed with some, but I found well, for me, it's striking that we never hear, we just hear the rise will be, well, it used to be half a meter before 2100, now it's between half a meter and 1 meter. In fact, NASA last week or recently said it will be of the order of 1 meter. But we never hear of what could come afterwards and what's the potential threat, which is something I think which is a very important message. And as I tell, that there are, because that's the problem we have as mathematicians. We study models, but the model only contains what we put in it. And that's where it's also a danger, I could say, because we put some varnish on science, and then so we have a responsibility, because we can say what the model will produce. And this is where we cannot work alone. We have to work with other disciplines. What do we put in our models? Have we forgotten something essential? So, well, that's what the data is. So, of course, what will happen with all this water, it's fun to start a discussion, but the data is we should look, if you just build your dams now to say, okay, they have to be, okay, we'll have 1 more meter in 2100, and then the storms will be stronger, but that's not enough to take your decision. You have to go much further. And the potential collapse, I was very impressed, the potential collapse of the West Antarctica ice sheet, which is something that the people are looking very seriously. And of course, okay, there are several scenarios for the global change. The 1 meter is if it's, okay, it could be more if the warming is more.